Hi, good morning students. I am Vaishaki Shah from LJ Institute of Engineering and Technology. Now in our subject which is called Fluid Mechanics and Hydraulic, we started the topic which is buoyancy and flotation. We derived the analytical method to determine metacentric height. Okay, now in today's lecture we are going to study some equilibrium condition for floating and submerged body. So let's start. First theory is condition of equilibrium of a submerged body. Now what do you mean by submerged body? Submerged. So the body which is immersed or submerged in water, that is your submerged body, and here we are going to study the equilibrium condition for submerged body. Okay, so let's start the first condition, and the first condition is for stable equilibrium. Now here for stable equilibrium we are considering a balloon which is completely submerged in the air. Remember that, submerged in the air. The lower portion of the balloon is filled with heavy material. So center of gravity is lower than center of buoyancy. As you can see in the first diagram, this is your center of gravity and this is your center of buoyancy. Now at this lower part, at this part, a heavy material is filled. Heavy material is filled. So center of gravity is below the center of buoyancy. Okay. Now the weight of the balloon is W, which is acting from G. G, that is center of gravity. Now weight of the balloon is acting from center of gravity, and which is W. W is weight of the balloon acting downward direction. And now buoyant forces, we indicate buoyant forces by FB, and buoyant forces are always acting in upward direction. So buoyant forces are acting from upward direction from point B. As you can see here, B is center of buoyancy and buoyant forces are acting in upward direction, weight acting in downward direction. Now for equilibrium of the balloon, here W equals to FB. W must be equals to FB for equilibrium of the balloon. Now if the balloon give small angular displacement in clockwise direction, as you can see here, if this balloon is given small angular displacement in clockwise direction, then W and FB forms a couple. W and FB forms a couple in anti-clockwise direction. Here you are giving displacement in clockwise direction, but W and FB forms a couple in anti-clockwise direction. So the balloon again brings to its original position, which is in stable equilibrium condition. So if W equals to FB, then point B is above G and the body is said to be in stable equilibrium. If W equals to FB, then point B is above G and the condition is called stable equilibrium. Clear? Now second condition, which is unstable equilibrium. Now for the unstable equilibrium, W equals to FB, and remember point B is below point G. For stable equilibrium, point B was above point G, but here center of buoyancy is below center of gravity. So the body is said to be in unstable equilibrium as shown in figure if you give small angular displacement to this body. This part is filled up with heavy liquid. Okay, and if you give small angular displacement to the body in clockwise direction, you gave displacement in clockwise direction, then W and FB forms a couple in clockwise direction only. W and FB forms a couple in clockwise direction. So balloon does not return its original position, so that's why it is in unstable equilibrium. Okay, balloon can't return on its original position, so it is in unstable equilibrium condition. Clear? Now third condition, which is neutral equilibrium. Now if W equals to Fb and B and G are the same points, here you can see that B center of buoyancy, G center of gravity, weight W is acting downward, buoyant force Fb are acting upward. Now W equals to Fb, here point B and G are the same points. So the body is said to be in neutral equilibrium condition. Neutral equilibrium condition. Clear? Okay. Now our next theory is condition of equilibrium of a floating body. Remember that, don't be confused. Here there are two theories. First is a condition. First we studied the condition for submerged body, and the second condition is for floating body. Don't mix that both theories. Okay. So let's start the theory of condition of equilibrium for a floating body. First of all, the stability of floating body, which is already floating. Okay, so floating body, the stability depends on metacenter. Where is the metacenter? So by location of metacenter, the stability of body is determined. So first condition here is stable equilibrium. Here as you can see in the first diagram, there is point B and there is point G. From point B, buoyant forces are acting in upward direction. From point G, weight of the body acting in downward direction. Okay. So if it is given small angular displacement, so this is your again axis, normal axis. Now in this case the body is tilted, so center of buoyancy shifted to B1. B1 is your new center of buoyancy, and if you draw a line passing from new center of buoyancy and old center of buoyancy which intersect at point, that is your metacenter. Here M is your metacenter. Okay. If M is above G, M is above G, so the floating body will be in stable equilibrium. If M is above G, then body is in stable equilibrium. Okay. If the slight displacement is given to the balloon, given to this body in clockwise direction, the center of buoyancy shifted from B to B1, such that vertical line B1 cuts to the point M, and where M is your metacenter. Then the buoyant force Fb through B1 and weight G through weight W through point G forms a couple which acting in anti-clockwise direction. Remember that here buoyant forces and weight of the body forms a couple which is in anti-clockwise direction, which brings the floating body into its original position, because M is above G. M is above G. So forms a couple which is in anti-clockwise direction and body returns to its original position. So this condition is stable equilibrium. Okay. In a stable equilibrium, as you can see that M is above G. M metacenter which is above G. Clear? Now second is unstable equilibrium. As you can see here, here is your first body where G is center of gravity, B center of buoyancy. Buoyant forces are acting upward direction, weight is acting in down. Here is your first body where G is center of gravity, B center of buoyancy. Buoyant forces are acting upward direction, weight is acting in downward direction. Now if this body is given small angular displacement, then line path there is a new center of buoyancy which is B1, and buoyant forces are acting from point B1 here. In this case M, that is your metacenter, is below center of gravity. M is metacenter which is below center of gravity. So if M is below G, the floating body will be unstable equilibrium if you given small angular displacement in clockwise direction. Then buoyant force is Fb and W forms a couple also in clockwise direction. In this case, W and Fb forms a couple in clockwise direction only. So that the overturning is possible here for the floating body. In this case, a floating body, there are so many chances that it overturns. So this is your unstable equilibrium condition, where you can see that also in that diagram, M, which is your metacenter, M is below G. M is below center of gravity. So where M is below center of gravity, the condition is unstable equilibrium. Clear? Now third condition is neutral equilibrium. Now if point M and center of gravity are at the same point, M is the center of gravity of the body. So here metacenter and center of gravity both are the same points. Then the body, your floating body, is in neutral equilibrium condition. Clear? So there are two theories, where first is condition of equilibrium for submerged body, and second is condition for equilibrium in floating body. Okay. So moving further to our next theory, which is experimental method for metacentric height. If you remember, then we already studied the method which is analytical method for determination of metacentric height. Now today we are going to study a method which is experimental method. Both methods are used to determine metacentric height, and metacentric height we know, which indicate as Gm. So here we will find out Gm, metacentric height, by experimental method. So let's start our theory. As you can see in this diagram, first there is a body and weight of the body acting in downward direction. Okay, G, that is center of gravity here, B, that is center of buoyancy here, and M is your metacenter. Okay. Now if this body is given small angular displacement here, so this is your normal axis, and this line is your line of new center of buoyancy and new center of gravity. In this case, remember that if you place a weight above the rectangular block, above this given block, and here if the weight already shift, body is tilting. If I am placing this here, and if your body tilts, then it comes to like this. Okay. So same way, if you place any weight here and your body tilts, then it comes to this place. Okay. And in this case, weight of the body is also changes, because weight firstly placed at center, then due to tilting weight comes to here. So weight of the body also changes. So there is change in center of gravity and center of buoyancy in both points. So here B1 is your new center of buoyancy, and G1, that is your new center of gravity. Center of buoyancy and center of gravity both displaced here. Okay. So now let's start our derivation. The metacentric height, here as we know that the block, the additional weight which we indicate as W1, is placed at center in your first diagram. Now in a second diagram, your body tilts, so weight is shifted from center to that side location, and that distance is x. So the metacentric height of the floating vessel can be determined by providing that center of gravity of floating vessel, let W1 is known as weight which is placed over center of the vessel as shown in figure. Now this is your enlarged diagram where G, that was your old center of gravity, G1 is a new center of gravity. Now the weight shifted here, the weight is shifted here, which is W1. So the distance between old center of buoyancy and new center of buoyancy is x. The distance between your original normal axis to weight is x. As you can see in that diagram, distance from center to shifting of the weight, that is x, and here weight of your body, which is W1. So W1 is moved across the vessel towards right through a distance x. Now the vessel will be tilted. So the new center of gravity will be shifted to G1. As the weight has been moved towards right, also the center of buoyancy will be changed to B1 as the vessel has tilted. Now under equilibrium, the moment caused by moment of load W through a distance x must be equals to moment caused by shifting of center of gravity to G2, G1. Now here, as this statement indicates that there are two moments. First moment is generated due to shifting of this weight W to W1, shifting of this weight. Now second moment is generated to shifting of center of gravity from G to G1, G to G1. So there are two moments generated here. First moment due to shifting of weight and second moment due to shifting of center of gravity. So here G, the moment due to change of G, that is from point G, total weight is acting. So moment, which is force into perpendicular distance. Now we have W, which is acting from point G, and its perpendicular distance is G1. Perpendicular distance is G1. As you can see in the diagram, W, which is weight acting from point G, and the distance is G1. If you apply the equation for tan theta here, you can see the angle theta. Then tan theta equation apply for tan theta, you get Gg1 equals to Gm tan theta. Gg1 equals to Gm tan theta. So now W1 equals to W1 into x. The moment due to moving of W1 into x, moment of shifting of weight, that is W into Gm tan theta, and second shifting of weight. Now the distance between old normal axis and weight is x, and we know the amount of weight, which is W1. So moment due to shifting, which is force into perpendicular distance. Now in this case, force is W1, which is weight, and it is shifted at angle at a distance x. So your new moment generated, that is W1 into x, weight into distance. So the moment due to that moment, which is W1 into x, both are equal and opposite. So W1 into x equals to W into Gm into theta. Now make Gm as your subject, Gm is your metacentric height. So Gm equals to W1 into x divided by W tan theta. Now this equation is experimental equation to find out metacentric height Gm. Gm, as you can see in the diagram, Gm is your metacentric height, and you can find out metacentric height by using this equation. W, here W is weight, additional weight, x, that is a distance of weight to normal axis, here capital W, that is weight acting downward direction, into tan theta. So this equation is an experimental method, equation by experimental method to determine metacentric height. So done for the today. In next lecture we will derive some more theories based on chapter called buoyancy and flotation. Thank you.